Think about that moment when a weak winter sun peeks through the clouds and you feel a surprising bit of warmth on your skin.
Mhm.
Or that, refreshing chill as you step out of a steamy shower.
Yeah, those everyday things, they really hint at something quite remarkable, don't they?
Exactly. The science of heat and its, well, constant transformations.
Huh.
And that's exactly what we're going to explore in this deep dive, based on what you've asked us to uncover.
Indeed. We'll be looking at heat not just as something we feel, but as a fundamental form of energy.
Okay.
We'll trace how it moves, understand how we measure it, and sort of reveal its often unexpected influence on the world around us.
So, like, why a seaside town feels so different from inland?
Precisely.
Yeah.
Or even just how an ice cube works its magic in your drink.
Hmm.
It all comes down to these core ideas.
Like specific heat capacity and latent heat? Stuff from the materials you shared?
Exactly those. We'll ground it all in that material.
Fantastic. So, our goal here is to really dig into the essential principles of heat transfer and its effects.
Yeah, make it make sense.
Right, but more than that, spark those aha moments.
Find the surprising connection.
Yes.
Yeah.
And the practical side, without getting bogged down in super technical jargon.
Sounds good.
All right, let's dive right in. What exactly is heat? Like, at its heart?
Well, fundamentally, heat is a form of energy.
Okay, energy.
It's the energy tied to the motion of atoms and molecules within a substance. Invisible, but we feel its effects constantly.
Right.
And the guiding principle of how it flows is pretty straightforward.
Right.
It always moves from hotter to colder. Always.
Hotter to colder? Like mixing hot and cold water?
Perfect example. The faster, hotter molecules bump into the slower, colder ones.
And they share the energy.
They transfer some energy, yeah, until everything evens out,
Uh.
reaches a shared temperature.
Like those two objects in the material, one at 80 Celsius, the other 30.
Mm-hmm.
If they touch, the heat just drifts from the hot one to the cool one.
Exactly.
Yeah.
Until they both hit the same temperature. It's that natural tendency towards balance. Thermal equilibrium.
Thermal equilibrium. Okay.
And there's a really clear link between heat and temperature. Usually when something absorbs heat energy.
Its molecules move faster.
Right. And we see that as a rise in temperature.
And the opposite if it loses heat.
Molecules slow down, temperature drops. Simple as that.
So how do we actually measure this energy, this heat we feel but can't see?
Good question. The amount of heat gained or lost, well, it depends on a few key things.
Okay, like what?
First, there's the mass of the object, how much stuff there is.
Right.
Imagine heating, say, 2 pots of water. Same flame, same time. But one pot has double the water.
The bigger pot won't get as hot.
Exactly. Same heat, but spread over more water molecules, so less temperature increase. Heat is proportional to mass.
Makes sense. More stuff needs more energy to heat up overall. What else?
The change in temperature itself, how much the temperature actually shifts.
Okay.
If you have two identical things and one gets, say, 10 degrees hotter while the other only gets 5 degrees hotter.
The one with the bigger change must have absorbed more heat.
Precisely. A bigger temperature swing needs a bigger energy transfer. So heat is also proportional to that temperature change.
Got it. Mass temperature change. And you said a third thing.
Yes, the nature of the substance itself, what it's actually made of.
Oh, right. Like heating water versus oil.
Exactly. Equal amounts, same heat source, same time. They'll end up at different temperatures.
So different materials handle heat differently.
They have different sort of appetites for heat. Some soak it up easily, others less so.
Okay. Mass, temperature change, and the material itself. So how do we put numbers on this? What are the units for heat?
The common units you'll see are the calorie and the kilocalorie.
Calorie, like in food.
Sort of, but specifically defined here. 1 calorie is the heat needed to raise 1 gram of water by 1 degree Celsius.
Just 1 degree.
Well, specifically from 14.5 degrees C to 15.5 degrees C. It's quite precise.
Okay. Add a kilocalorie.
Just 1,000 calories, often called a calorie with a capital C, confusingly. That's the heat to raise 1 kilogram of water by that same 1 degree Celsius.
Right. And since heat is energy, it must link to the standard energy unit, the joule.
Absolutely. They're directly related. 1 calorie is about 4.2 joules.
So 1 kilocalorie would be 4,200 joules?
Roughly, yes. And conversely, 1 joule is about 0.24 calories. They're just different scales for the same thing. Energy.
Now, this idea that different materials handle heat differently, that brings us to specific heat capacity. Sounds technical, but it seems important.
Oh, it's hugely important and actually quite intuitive. Think about the beach again, sand and water.
Right, sand gets burning hot, water stays coolish.
Even though they get the same sunlight.
Yeah.
Right. That's specific heat capacity in action.
So it's like how much heat something can take before its temperature really changes.
That's a great way to put it. It's the amount of heat energy needed to raise the temperature of a unit mass, like 1 kilogram of a substance by 1 degree Celsius.
Unit mass, so it's a property of the substance itself.
Exactly. It's like a measure of how resistant that substance is to changing temperature when you add or remove heat.
Yeah.
We often use a capital C for it.
And the units for this specific heat capacity.
In the standard SI system, it's joules per kilogram per Kelvin. JKGRK.
Kelvin, why Kelvin?
Well, a 1 degree change is the same size in Celsius and Kelvin, so practically you'll often see it as joules per kilogram per degree Celsius too. JKDRK?
Or even per gram sometimes, JD or gear.
Yep, you see that too, especially for smaller quantities.
Okay. The source material gives examples. Water is way up there at 4,200 JKB gear.
Huge, isn't it?
Yeah, compared to like kerosene oil at 2,100 or mercury way down at 139. Iron's about 483.
That massive value for water is, well, it's incredibly significant.
What does it mean practically that water's number is so high?
It means water can absorb a ton of heat energy without its own temperature shooting up. And conversely, when it cools down, it releases a lot of heat.
Mm-hmm.
It's like a thermal buffer.
Thermal buffer, I like that. So how does that play out?
Think about coastal climates, land and sea breezes.
Okay.
During the day, land heats up much faster than the nearby water, right? Lower specific heat.
Yeah, sand gets hot fast.
So the air above the land gets hot, rises,
yeah,
and cooler air rushes in from over the sea to replace it.
that's the sea breeze.
That's the sea breeze. And at night, the land cools down quickly.
But the water stays warmer for longer.
Exactly, because it's high specific heat. So now the warmer air is over the sea, it rises, and cooler air flows from the land out to sea.
The land breeze, wow, it's all driven by that difference.
All driven by water's high specific heat capacity. It moderates coastal temperatures. And the oceans themselves. Huge heat reservoirs regulating the whole planet's climate.
Incredible. Just from that one property. What else?
How about a hot water bottle? Why does it work so well?
Because the water stays hot for a long time.
Precisely. It holds a lot of heat and releases it slowly. High specific heat means it takes ages to cool down significantly.
A thermal sponge, you called it.
Yeah, soaking up heat and letting it go gradually.
Makes sense. And car radiators use water too, right?
Same principle. Water can absorb a lot of heat from the engine. For every degree its own temperature rises, more than most other liquids. It carries away that excess engine heat very effectively.
So it keeps the engine from overheating. Okay. What about keeping things cold?
Well, think about preventing drinks from freezing in winter. Some people put bottles in water.
Why does that help?
Because the water cools down slowly, it acts as a buffer, it slows down the rate at which the juice or wine inside the bottle loses heat, preventing it from freezing too quickly.
Ah, protecting it, like farmers flooding fields before a frost.
Same idea. The water releases heat as it cools, and even more if it starts to freeze, which helps keep the air temperature around the crops just above freezing. A bit of protection.
Clever. And cooking pans, they're usually metal, low specific heat.
Generally, yes. Metals like copper, aluminum, iron. They have low specific heat, and they're good conductors.
Good conductors meaning heat moves through them easily.
Right. So they heat up quickly, don't need much energy for a big temperature jump, and the heat spreads evenly across the bottom. Ideal for cooking.
Okay, this is really connecting the dots. Now, the formula. Q is MECEZR. Let's break that down.
Sure. Q is the heat energy transferred.
Okay.
M is the mass of the substance.
How much of it?
C is that specific heat capacity we just talked about, the material's property.
Got it.
And delta T,
Yep.
is just the change in temperature, the difference between the final and initial temperature.
So if you know the mass, the material, its C value, and how much the temperature changed, you can calculate the heat, Q.
Exactly. Or if you know the heat added and the mass of material, you can figure out the temperature change. The examples in the source, like heating an iron bar or finding the temperature rise of lead, they all use this.
And it works with calories or joules, just need to be consistent.
Right. Know any three, find the fourth.
Okay. Now, you said specific heat capacity is about the substance, but what about a whole object? Is there a difference?
There is. We sometimes talk about just heat capacity or thermal capacity.
Not specific heat capacity.
Yeah.
Right. Heat capacity is the heat needed to raise the temperature of the entire object by 1 degree Celsius.
The whole thing, regardless of mass.
Well, it depends on the mass. It's basically the object's mass times its specific heat capacity.
Ah, okay. Heat capacity equals MEC.
Yep. So a bigger block of iron will have a higher heat capacity than a smaller block, even though the specific heat capacity of iron itself is the same.
Got it. Specific is per unit mass. Heat capacity is for the whole object. Makes sense.
Specific heat is about the material. Heat capacity is about the specific body or object.
Clear. Now, what happens when you mix things? Hot object, cold object together. That's calorimetry.
Yes, the principle of calorimetry. It's fundamental to understanding heat exchange.
What is the state?
Simply put, when things at different temperatures touch, heat flows from hot to cold until they reach the same temperature.
Equilibrium again.
Right. And crucially, if no heat escapes to the surroundings.
Like in an insulated container.
Ideally, yes. Then the heat lost by the hot object equals the heat gained by the cold object.
Heat lost equals heat gain.
That's the core idea, conservation of energy applied to heat.
Like the example of dropping hot copper into cool water.
Exactly. You calculate the heat the copper loses as it cools, set it equal to the heat the water gains as it warms up.
And you can figure out the final temperature they both end up at.
Precisely. Using their masses, their specific heat capacities, and that Q equals MC formula for both.
Okay, that makes sense. Now, we've been talking about temperature changes within a state, like heating water. What about changing state itself? Melting, boiling.
Ah, phase changes. Yes, that's where things get really interesting.
A change of state is just solid to liquid, liquid to gas, and back.
Exactly. Melting ice to water, boiling water to steam, or the reverse, condensing steam to water, freezing water to ice. These are triggered by adding or removing heat.
The source also mentions sublimation, solid straight to gas.
Like dry ice, yeah. And the reverse, deposition, gas straight to solid, all phase changes.
And during these changes,
Oh,
the temperature does something weird, right?
it stays constant. That's the key point.
Yeah.
While ice is melting, it stays at 0 degrees C, even as you're adding heat.
So the heat isn't making it hotter. Where's the energy going?
It's going into breaking the bonds, holding the molecules together in the solid structure, changing the phase, not the kinetic energy, not the temperature.
Fascinating.
Yeah.
And the source highlighted that weird thing about water. Ice floats. It expands when it freezes.
Yes. That's incredibly unusual. Most substances contract when they solidify. Water expands.
And that has big consequences. Burst pipes, potholes.
Definitely those. The expansion force is huge. It breaks rocks, affects soil. But think bigger.
Okay.
If ice didn't float, if it were denser than water, lakes and rivers would freeze from the bottom up.
And everything living in them would die.
Pretty much. The surface ice layer acts as an insulator, protecting the liquid water below. Aquatic life depends on ice floating. It's crucial for ecosystems, even climate.
Wow. Never thought about floating ice that way.
Yeah.
So that graph showing ice heating up, it starts at about 10 degrees C, it goes up to 0 degrees C.
Then it flattens out at 0 degrees C while it melts. That's a plateau.
Right, the temperature pauses. Then the liquid water heats up to 100 degrees C.
And flattens out again at 100 degrees C while it boils into steam. Another plateau.
So those flat parts are where the phase change is happening and the heat energy isn't raising the temperature.
Exactly. That energy being absorbed during the phase change without changing temperature, that's called latent heat.
Latent heat. Hidden heat.
Precisely. The term comes from Joseph Black, a Scottish scientist. Latent, meaning hidden. It's the energy used just to change the state.
And we see it working, like ice cooling a drink. It's not just the coldness, but the melting.
Right. As the ice melts at 0 degrees C, it absorbs a lot of latent heat from your drink, cooling it down much more effectively than just 0 degrees C water would.
And the greenhouse example. Water freezing releases heat.
Yes, as water freezes, it releases that latent heat back into the surroundings, which can help keep the greenhouse temperature from dropping too low.
So there's latent heat for melting, freezing, and for boiling, condensing.
Correct. We call it the specific latent heat of fusion, LF, for the solid-liquid transition.
Fusion, like melting.
Melting or freezing, yes. And specific latent heat of vaporization, LV, for the liquid-gas transition. Boiling or condensing.
Specific latent heat. So again, it's per unit mass.
Yes. The amount of heat needed per kilogram or per gram to change the state at a constant temperature.
The source gave some values. I think they were a bit mixed up, though.
Yeah, the units seemed off. Typical values are more like, for ice melting, LF, it's around 334,000 joules per kilogram, or 334 Jagger.
Okay, if 334 Jagger for melting ice, that's quite a bit.
It is. And for water boiling, LV, it's even higher, about 2,260,000 joules per kilogram.
Whoa, that's huge. 2,060 joules per gram.
Yep. 2260 Jagerbrand takes a lot of energy to turn liquid water into steam, even once it's already at 100 degrees C.
So melting and boiling absorb energy, they're endothermic.
Correct. And freezing and condensing release that same amount of energy, they're exothermic.
And the formula for calculating this heat is Q equals MAL.
Simple as that. Heat Q equals mass. M times this specific latent heat, L. Either L for LV, depending on the process.
Got it. And the units for L are joules per kilogram, JKG, or joules per gram, JG.
Right. The examples calculating heat for melting ice or condensing steam, just use that formula.
Okay, so these big latent heat values for water, they must have real-world impacts too.
Absolute huge impacts. Take the latent heat of fusion of ice first.
The 334 JG one.
Right. Because it's so high, mountain snow melts gradually.
Ah, preventing floods.
Exactly. If
Yeah.
L for tiny, it would all melt in a rush. And lakes freeze slowly, releasing that latent heat, moderating local temperatures, protecting life below the ice.
And makes ice better at cooling drinks than cold water.
Because it absorbs all that extra heat just to melt.
Okay, what about the massive latent heat of vaporization for steam, the 2260 JK?
That's why steam burns are so much worse than boiling water burns.
Even at the same temperature, 100 degrees C.
Yes. When that 100 degrees C steam hits your skin, it first condenses into 100 degrees C water, releasing that enormous 2260 joules for every single gram. Then you have the heat from the hot water itself.
Ouch! So it delivers a double whammy of heat.
A massive extra dose of energy. That's also why steam was used to power engines' huge energy release upon condensation.
And it helps keep soil moist.
Yeah, because it takes so much energy for water to evaporate, the process is slower, helping plants retain water.
Okay. Now, the source distinguished evaporation from vaporization, or boiling. They're not the same.
Not quite, though both turn liquid to gas. Key differences.
Like?
Evaporation can happen at any temperature below boiling. Boiling only happens at the boiling point.
Yeah.
Evaporation is slow, happens only at the surface.
Yeah.
Boiling is rapid, happens throughout the liquid, you see bubbles form inside.
And evaporation causes cooling.
Yes. The fastest, highest energy molecules escape from the surface, leaving the average energy, and thus the temperature of the remaining liquid lower.
But boiling doesn't cool the liquid itself because you're constantly adding heat.
Exactly.
So what makes things evaporate faster?
Several things. Higher liquid temperature, hotter water evaporates faster.
Makes sense.
The nature of the liquid petrol evaporates way faster than water. Weaker forces between molecules.
Right.
Surface area. Spread it out thin, like in a saucer versus a cup, it evaporates much faster. More surface exposed.
Okay.
Airflow. Wind blows away the vapor near the surface, letting more escape.
Like drying clothes on a windy day.
Yep. Also, surrounding temperature and humidity. Hot, dry air helps evaporation.
Like spreading clothes in the sun, or why things dry faster even on a cold, dry winter day sometimes.
All those factors play a role.
And we use that cooling effect of evaporation all the time, don't we?
We do. Wet cloth on a forehead.
Cooling tea in a saucer.
Earthen pots keeping water cool. The water seeps through pores and evaporates from the outside surface.
And sweating. Our body's cooling down.
Crucial biological process. Evaporation carries heat away from our skin.
Amazing. And boiling point. You said it's when the vapor pressure equals atmospheric pressure?
That's the technical definition, yes. As liquid heats up, its molecules push outwards more. That's vapor pressure. When that push equals the air pressure pushing down, the liquid can boil throughout.
So boiling point depends on air pressure.
It does. Lower pressure, like high up a mountain, means a lower boiling point. Higher pressure, like in a pressure cooker, means a higher boiling point.
Fascinating. Okay, last topic. Conductors and insulators. Heat movers and heat stoppers.
Pretty much. Good conductors let heat flow easily. Metals are the classic example. Silver, copper, aluminum, iron.
Silver's the best.
Generally, yes. It's because metals have lots of free electrons that can easily carry thermal energy around. Mercury's a decent liquid conductor, too.
And insulators. Bad conductors.
They resist heat flow. Glass, wood, plastic, wax, air, wool.
Air is an insulator.
A very good one, actually. That's why trapped air is used in things like double glazing or thermal clothing. Gases are generally terrible conductors. Ebonite, asbestos are extreme insulators.
And mica. Good heat conductor, bad electricity conductor.
Yet, some materials have interesting combinations of properties.
And is there a link between conductivity and specific heat?
Generally, yeah. Good conductors, like metals, tend to have low specific heat capacities. They heat up fast and transfer heat easily.
And insulators.
Often have high specific heat capacities. They resist temperature changes and resist heat flow. It often goes hand in hand.
Right, that covers a lot of ground. Let's try and wrap up the key takeaways from this deep dive.
Okay, so first, heat is energy, always moving from hotter to colder. Simple, but fundamental.
Right. And how much heat moves depends on mass, temperature change, and the material's specific heat capacity.
Yep. Water's high specific heat is super important for climate, cooling, all sorts.
Then there's phase changes, melting, boiling, where latent heat comes in.
Energy used to change state, not temperature. Again, water's high latent heats are critical. Ice melting slowly, steam carrying lots of energy.
We sorted out evaporation surface cooling versus boiling blow change at a specific temperature.
And how factors like temperature, surface area, and airflow affect evaporation.
And finally, conductors let heat pass easily, insulators block it, metals good, air bad.
Connected often to specific heat capacity. That covers the main points, I think.
Definitely. Hopefully this deep dive gave you, our listener, a clearer picture of these heat concepts and maybe sparked some of those aha moments about how relevant they are every day.
Yeah, connecting the physics to the experience.
Exactly. So final thought for you to chew on.
Mm-hmm.
We talked about how high water specific heat and latent heats are. What if they were much lower?
Interesting question.
How different would Earth be? Think about climate, weather, even just how our own bodies work. If water heated up really easily and changed state with hardly any energy...
That would be a radically different world. Definitely something to ponder.